In this video we will look at a group of experiments involving liquid nitrogen. Liquid nitrogen is obtained by the fractional distillation of liquid air. Nitrogen gas is odorless and colourless, and if you drop its temperature down to minus 196 degrees centigrade, it becomes a liquid. Liquid nitrogen itself is odorless and colourless. Minus 196 degrees centigrade is roughly 220 degrees colder than the air. This poses a few problems for those people needing to use liquid nitrogen. Liquid nitrogen is a cryomaterial and it will cause burns, cold temperature burns. Cautions have to be taken. Now, you cannot use normal glassware to hold liquid nitrogen. What I'm doing here is pouring liquid nitrogen from a metal flask called a dewar into a glass version. This essentially is one beaker inside the other, but with the air gap between the two pieces of glass being removed. The vacuum between the inner and outer skins of the glass dewar allows no heat to be conducted or convected. Let's just consider the white stuff that comes off the top of the liquid nitrogen. It can't be liquid. Nitrogen gas, which makes up 78% of the air, is certainly not white. What we're seeing here is the effect of the cold nitrogen gas leaving the dewar, hitting the air. The air is full of water vapor, and that water vapor is condensing down to billions upon billions of tiny droplets of liquid water. We can use the low boiling point of liquid nitrogen to produce liquid oxygen. Liquid nitrogen boils at minus 196 degrees centigrade. Liquid oxygen's boiling point is slightly higher at minus 183 degrees centigrade. Here we simply put some liquid nitrogen into the Fanta can, and the oxygen from the air condenses on the outside of the very cold surface and drops into the watch glass below. The simple test for oxygen is that it relights a glowing spill. And here we can see that the liquid condensing off the tin also relights a glowing spill, so it can't be water. It's oxygen in its liquid state. Let's take a look at what happens when rubber tubing is placed in liquid nitrogen. There's a lot of science going on here. The heat from the rubber tubing, which is at room temperature is 220 degrees above the boiling point of liquid nitrogen. Some of that heat gets transferred into the liquid and is used to overcome the weak intermolecular bonds that hold the liquid particles together and turns it into a gas. The gas comes out of the rubber tubing, pushing with it any unsuspecting drops of liquid nitrogen that get in the way. Since the rubber tubing is giving up its heat energy, the rubber tubing itself becomes cold. Rubber is a polymer, long chains of molecules. At room temperature, these molecules can slide past each other slightly, hence the rubber tubing is bendy. If you remove that energy, the rubber tubing can no longer have its molecules slide past each other, and they become more rigid. The rubber tubing becomes more rigid. The molecules are in a more fixed position. Hence we have a change in physical properties of the rubber tubing. Let's put a long rubber tube of air into the liquid. The air in the part of the balloon that's in contact with the liquid can cool down. So if we want all the air to cool down, we've got to force it down into the liquid. Why does this happen? Liquids at lower temperature take up less volume. Their particles are less free to move about, and so they do require less room. The balloon therefore contracts. If we take the chilled balloon out of the liquid nitrogen into the air being 220 degrees warmer than the liquid, the particles gain energy, gain movement energy, and expand. The individual particles in the air, the atoms and molecules, don't expand, they simply move further apart. It's the bulk property of the volume of the air that gets bigger. We can show this in a slightly different way. We've tethered a balloon to a side-arm conical flask. The side-arm conical flask originally is at room temperature. We put in about 35 cubic centimeters of liquid nitrogen. If it were accurately measured, that would actually be 1 mole of nitrogen, 1 mole of N2, 28 grams. The heat from the flask causes the liquid to boil, The gas produced fills up the balloon until the balloon can't withstand its internal pressure anymore and explodes. It should be noted that 1 mole of any gas at room temperature and pressure occupies a space of 24,000 cubic centimetres or 24 cubic decimeters. There's a lot of empty space between particles in a gas compared with particles in a liquid. Putting a banana half in and half out of liquid nitrogen might seem bizarre, but it shows you some unusual properties of a banana. If we leave the banana in liquid nitrogen for a while, eventually the lower half of the banana will cool down, as will be seen by the lowering of the amount of bubbles of liquid nitrogen around it. If you take the banana out, you can demonstrate easily with a hammer the difference in properties with the banana that has been cooled down to one that's still at room temperature. Bananas are not conductors of heat, otherwise the entire banana would crack as brittly as the lower half. The reason for this should be obvious, but bananas are, like we are, made up mainly of water. The water in the cells, the cytoplasm, simply freezes at -196 degrees centigrade. The same happens in an egg. Whilst the egg in liquid nitrogen looks like it's frying, it's not actually a fried egg. When you fry an egg, there are chemical changes that turn the protein in the egg white and the egg yolk into different forms of protein that do not go back to the original state once they are fried. What we're doing here is simply freezing down the proteins in the egg white and the egg yolk, and it looks like a fried egg. If this frozen egg were allowed to come back to room temperature, it would be runny again.